Most agricultural crops grown today are exposed to pesticides, fungicides, and herbicides. Organically grown crops are thought to be free of man-made chemicals. How can we monitor the presence or absence of these chemicals in the food we eat?
Many agricultural chemicals wash into nearby lakes and streams and may affect wildlife. How can we determine when and where these chemicals enter an aquatic system?
Over-the-counter medications are monitored to ensure consistent concentrations of the active ingredient in each tablet. However, herbal supplements are not regulated, and there is considerable concern over how accurate the product labels are. One recent study by a student at Whitman College found that the dose of hypercin per tablet varied widely in different brands of St. John's wort. How can we measure the quality of these products?
The answer to these questions is chromatography. Chromatography is a two-part process. First, the complex mixture of chemicals must be separated into individual constituents. Next, each chemical must be detected. A simple illustration is the separation of black ink by thin layer chromatography. Here, the separation process results from attractions between the cellulose fibers and the different ink compounds.
Given the huge number and types of organic compounds that have been documented, it is not surprising that a wide range of chromatographic techniques exist. These can be divided into three basic types: gas chromatography, liquid chromatography, and supercritical fluid chromatography. We will focus on liquid chromatography.
Liquid chromatography can be divided into more specialized forms of chromatography, with each form being useful in the separation of different classes of compounds. Each of these liquid chromatography techniques have found a unique niche in separation science since they allow the separation of non-volatile species and thermally fragile compounds.
Exclusion chromatography, which can be subdivided into gel permeation and gel filtration, operates based on separation by size, as the name implies. This is traditionally used in the identification and purification of large biomolecules.
Ion exchange operates by using an analytical column to separate the ions and a suppressor column to absorb any counter ions released into solution. Both cations and anions can be analyzed. The mode of detection is a conductivity device.
Adsorption chromatography, also called liquid-solid chromatography, is used to separate compounds with molecular weights below 5,000. Solid silica and alumina beads serve as the stationary phase, and the only variable to optimize the separation is the polarity of the mobile phase.
In this video, we are most interested in partition chromatography, where we can vary the selective nature of the solid or stationary phase and the liquid or mobile phase. This gives us great specificity in devising a separation scheme. Partition chromatography was originally developed using what is now called normal phase conditions. Here, the solvent tends to have low polarity, such as hexane or dichloromethane, and the solid phase is polar. The most common form of partition chromatography is referred to as reversed phase. Analyte separations are made using nonpolar stationary phases and relatively polar mobile phases.
Under the conditions used in normal phase chromatography, the least polar compound is transported or eluted first from the column due to it being the most soluble in the mobile phase. In reversed phase chromatography, the most polar compound appears first, and increasing the polarity of the mobile phase increases the elution time of this compound.
One of the first parameters that we need to discuss in chromatography theory is resolution. Whenever possible, we would like to obtain baseline resolution, which simply means that the detector baseline returns to zero between two adjacent peaks. There are also a number of terms that we need to define. T sub m is the time required for liquid or a non-retained tracer to travel from the injection system to the detector. T sub Ra is the retention time of compound A, which again is the time required for the compound A to travel from the injector to the detector. T sub R' A is the corrected or net retention time of compound A and is equal to T sub Ra minus T sub m.
Similar terms are used to describe the retention time of compound B. We calculate the resolution using the compound retention times and the width of the peaks at the baseline. For the two adjacent peaks shown here, we average the baseline widths. The simplest form of the resolution equation is shown here. An example of adequate resolution can be illustrated by imagining a mixture of two compounds being added to one end of a column. As the compounds are pushed down the column by the mobile phase, they start to separate due to differences in interaction with the stationary phase. The longer the column, the more time the compounds have to separate into two peaks.
There are a number of factors affecting the resolution of a chromatography system. The most simple to understand is nature of the packing in a column. Two column packings are illustrated here. The top column is a poorly packed column due to the relatively void spaces between the solid support. The column on the bottom is adequately packed. Note the flow patterns through the columns. The properly packed column allows the mobile phase to pass through the column with minimal dispersion, illustrated here by the width of the bar at the front of the flow path. This is also referred to as laminar flow. Although it is not shown here, the velocity gradient across the column is parabolic in shape. The fastest moving liquid would be in the center of the column, and the slowest moving liquid would be at the column wall. The region at the column wall is referred to as the no-flow boundary, since the mobile phase molecules immediately adjacent to the column wall are not moving.
In contrast, the poorly packed column shows considerable mixing. This is illustrated by the erratic flow lines and the relatively wide bar at the front of the migration front. Few chromatographers actually pack their own Hplc columns. Columns are commercially available for most separations, and only the most highly specialized researchers need to prepare their own solid support and pack their own columns.
There are a number of common stationary phases for reversed and normal phase chromatography. This variety of stationary phases allows for the separation of most organic compounds.
Another common source of poor resolution is mixing at tubing or component connection. The top figure illustrates how a proper fitting connection should be made. The ends of each piece of tubing should be as close to perfectly even as possible. When this is done, the flow conditions in the tubing remain laminar and dispersion is minimized. However, when the tubing ends are uneven or when they do not adequately meet, the laminar flow lines are disrupted and turbulent mixing occurs. This increases the dispersion, and if this type of connection occurs after the sample has been introduced to the system, poor resolution will result. The flow rate of liquid pushed through the column and the quality of the column packing come together to affect resolution. In order to mathematically relate these parameters to resolution, represented by R sub s, we must first develop a concept known as H, the theoretical plate height equivalent. To understand the naming of this parameter, we must go back to its origin in the petroleum industry. In petroleum refineries, the complex mixture of crude oil is separated by distillation. The mixture is heated up, compounds travel up the cooling tower, and groups of compounds separate based on their boiling points. The compounds with the lowest volatility, or high boiling point, condense first and are collected on the lower plates of the cooling column. The more volatile compounds rise higher in the column, finally cool, and are collected by the higher plates. The concept of the plate was developed in order to judge the quality of the cooling column and the point at which a given class of compounds is collected. For example, how many plates are required to separate diesel fuel from gasoline? This concept, although slightly dated, is used to estimate the quality of all chromatography columns. In chromatography, we are concerned with the width of the compound band as it passes through the column. The width of the band is analogous to the theoretical plate height. The narrower the band, the thinner the plate, and the better the resolution. Also, thinner theoretical plates allow more plates to be present in a column.
Let's think about the plate concept a little further. The thickness of the plate is influenced by the linear velocity of the mobile phase in the column. This is calculated by taking the volumetric flow rate and dividing by the cross-sectional area.
Note the relationship between the flow rate in the column and H. Thus, one goal of setting the flow rate is to keep H as small as possible. As stated earlier, the reason for this is the thinner the plate, the higher the number of plates that can be packed in a column. The total number of plates that can exist in a column is referred to as N. Now we have two parameters that relate conditions in the column to resolution. Low values of H are desirable and are highly affected by the flow rate. High values of N are desirable and are affected by the thickness of H and the length of the column. The longer the column, the more theoretical plates we can put in a column, and the better the resolution will be.
This type of column analysis is referred to as a Deventer plot and is the result of a number of factors, each affecting the value of H. These include 1. The multi-flow path effect, represented by line A, 2. The longitudinal diffusion, represented by line B, and 3. The mass transfer between the solid phase and the mobile phase, represented by the C line.
Note that decreasing the linear velocity allows molecules to diffuse more and broaden their peak width. Higher velocities push the compound through the column before diffusion becomes significant. In contrast, increasing the linear velocity results in a smearing of the peak in the column. This occurs when the compound is not completely transferred from the mobile phase to the stationary phase, and vice versa, before it is swept down the column. Thus, a compromise between these two processes must be found. This compromise is represented by the last line in this figure. Note that for most HPLC columns, a linear velocity between 0.1 and 0.3 centimeters per second is optimum.
The temperature of the column can also affect the resolution and elution time of each compound, but this is usually of minor consequence. Peak identification is made based on retention time in the system. Changes in the ambient temperature affect the mobile phase viscosity and analyte affinity for the solid phase, which in turn affects retention time. By controlling the column temperature, shifts in retention time due to diurnal temperature changes in the lab can be minimized.
Another important factor influencing the separation and resolution of a column is the composition of the mobile phase. This is illustrated by the general elution problem. For example, say that we have 6 compounds that we wish to analyze at the same time. The top figure illustrates a chromatogram resulting from the use of the single and consistent mobile phase. This type of setup is referred to as an Isocratic Gradient. Here the first 4 peaks are separated and have adequate peak shapes, but the remaining 2 are too broad for the integrator to adequately calculate the peak height or peak area.
However, if we change the mobile phase composition to one that allows the adequate separation of peaks 5 and 6 and allows for adequate peak shapes, we lose resolution of peaks 1 and 2.
The way to solve this problem and allow for the analysis of all compounds in the same chromatogram is to use a solvent gradient program. Here the solvent composition is consistently changed over the chromatographic run. For example, one may start the analysis with an 80% methanol and 20% water solution, and slowly change this to a 50-50 mixture by the end of the run. This can allow for the adequate separation and quantification of all 6 peaks, as illustrated by the bottom chromatogram. A basic HPLC system consists of a pressurized gas cylinder, mobile phase reservoirs, an autosampler, sample injection system, high-pressure pumping system, guard column, analytical column, detector, and data processing station. Selection of the mobile phases varies depending on the application, but once the proper gradient has been selected, they are all handled as follows.
We will start with a degassed solvent that serves as the mobile phase. Solvents can be degassed by vacuum filtration or by purging with helium gas. Filtration is also used to remove any fine particles that will cause undue wear of the piston and piston seal in the pumps.
The Dynex system illustrated here has frits attached to the intake of the solvent lines to remove particles. These solvent bottles are pressurized with helium to remove dissolved atmospheric gases such as oxygen and nitrogen that can form bubbles in the pump or detector and interfere with an analysis. Some systems also use the helium pressure to drive components of the system, such as the automatic injector or autosampler.
A variety of materials can be used in the manufacture of tubing to connect different components of the system. Low pressure points in the system can use Teflon as well as the standard stainless steel. Even more elaborate systems use materials such as titanium or PEEK. The system shown here uses PEEK in order to minimize contact with metal surfaces. PEEK is short for polyether ether ketone. This material is important when working with compounds that may be deactivated by metal surfaces, as in the analysis or preparation of enzymes. A variety of other materials have also been used to construct components such as pump heads, pistons, pump seals, and detectors. Pump heads are typically constructed of stainless steel, titanium, or PEEK. Pistons are usually composed of sapphire, but PEEK has been used as well.
In the past, HPLC systems had a separate pump for each solvent reservoir. This design significantly added to the cost of the systems, especially if the composition of the mobile phase was changed during an analysis, such as in a gradient elution. Many modern HPLC systems use a proportioning valve to adjust the mixture when more than one mobile phase is used. The proportioning valve in this system is located on the right side of the screen. It can adjust the composition of the mobile phase for up to 4 different reservoirs.
It should come as no surprise that high-pressure chromatography requires a high-pressure pump. 2 basic pumping systems have been used. The most inexpensive version is a syringe pump. The drawback to syringe pumps is that they only hold a limited volume of mobile phase, and they must be refilled periodically, usually before a series of analyses can be performed. The dual reciprocating pump is somewhat of an engineering accomplishment. Its design allows for a near constant flow rate at pressures ranging from 700 pascals to over 35,000 pascals. In order to illustrate how the pump works, we will use an animation. First, let's identify the components. Note that there are two identical pumping units, one on the left and one on the right. Solvent enters the system through the inlet at the bottom of the pumps. The solvent passes through an inlet check valve. The piston is a green-colored cylinder to represent the use of sapphire in actual pumps, and has a typical volume of 100 microliters. Another check valve is located at the outlet of the pumps. The pump outlets are connected by a T-union, which passes the flow onto the 6-port valve.
Now focus on the left side of the figure. As the piston retracts, it pulls solvent into the pumping chamber. The inlet check valve is designed to allow solvent to pass upward in the system while the outlet check valve is closed during the filling operation. The check valves are very simple in design. The actual check mechanism is a ruby sphere that positions itself in a concave, funnel-shaped seat when it is in the closed position. Solvent flow traveling in the upward direction raises the ruby sphere and allows solvent to pass. When the pump reverses itself and draws solvent into the pump chamber, the top check valve closes and the bottom one opens.
Now notice the pumping system on the right. It is identical in construction, but its piston operates exactly opposite to the one on the left. As one piston is pulling solvent into the pumping chamber, the other piston is pushing solvent to the 6-port valve and onto the column. In addition, the motor has a camming device that provides a constant flow rate by speeding up one piston as the other one slows down.
The pumps require maintenance from time to time. The most common maintenance operation is to clean the piston and replace the pump seals. It's time to do this when there are leaks around the pump, unstable back pressures, or no flow exiting the pump. We will illustrate how to clean and replace the pump seals with an older stainless steel single pump head system.
First, the inlet Teflon tube from the solvent reservoir is removed. Next, the bottom check valve is unscrewed. Then the effluent tubing from the pump is disconnected. The top check valve is removed. The bottom and top check valves contain the ruby sphere that moves up and down depending on the flow direction as seen in the previous diagram. Next, the pump head is removed. This must be done carefully because if the head is not removed evenly, it can break the piston. After the spacer and spring are removed, you can view the piston. The spacer holds the seal that must be replaced. After replacement of the pump seal and other worn parts, the pump is reassembled in reverse order to the disassembly steps.
Proper maintenance, such as filtration of all mobile phases and samples through a 0.45 microliter filter prior to injection, pumps can last years without problems.
After flow exits the pump, it enters a gradient mixer that ensures that the mobile phase is completely mixed.
Next, the flow travels to the 6-port valve and injector assembly. The valve is either in the load position, where samples are loaded into the sample chamber, or in the inject position, where the mobile phase enters the sample loop and forces the sample onto the guard column.
As you might expect, the 6-port valve has 6 ports connected to various components of the system. We will present these in the order that a sample would enter the system. Port 6 is where samples enter the valve, either from the autosampler or by a manual injection. Ports 1 and 4 are connected to the sampling loop and allow for the loop to be filled under ambient pressure. Sampling loops come in a variety of sizes, typically ranging from 5 to 250 microliters for analytical separations. Excess sample leaves the system out of port 5 and goes to a waste collection bottle. The mobile phase from the pump enters in port 2 and bypasses the sample loop, continuing on to the guard column.
Guard columns are used to protect the more expensive analytical column from destructive dissolved compounds in the sample, and from particles that may be present in the sample if it was not filtered prior to injection. Guard columns come in a variety of forms. Some have elaborate holders, while others are simply a short version of an analytical column. The stationary phase inside the guard column can range from silica particles to particles coated with the same reactive phase present on the analytical column. Mobile phase exiting the guard column is transferred to the analytical column, shown here. Selection of the stationary phase in the column is just as important as selection of the mobile phase composition. There are a variety of normal and reversed phase supports available from commercial vendors. The stationary phases shown here provide for the separation of a variety of compounds based on the compound's chemical structure and polarity. If the compounds are adequately separated in the analytical column, they exit the column one at a time and pass on to the detector.
The most common and versatile type of detector in use today is the UV Vis Detector shown here. This operates similar to the Spec 20 that you used in high school or in general chemistry, but allows sample to continuously flow through the system. The popularity of the UV Vis Detector is due to its near universal detection of organic compounds. The most common wavelength used is at 280 nanometers, but other wavelengths are used depending on the structure of the compound. Other detectors are available that offer more specificity for compound identification.
Now that the system has performed its job of separating and detecting each compound, we must process this data into information that we can use. Earlier data processors were as simple as the strip charts shown here. When these were used, lab technicians would triangulate the area under each peak, or, more commonly, measure the height of the peak with a ruler. Later, electronic integrators, such as the Hewlett-Packard version shown here, were used to automatically calculate the peak height and peak area. These work well for symmetrically shaped peaks that do not overlay with other peaks, but provide minimal control over integration parameters.
The availability of relatively inexpensive computers has made data processing much easier and provides the user with much more control over the way peaks are integrated. For example, it is not always possible to completely separate all compounds in an Hplc system. If the peak of interest is a shoulder peak, even after the system has been optimized, determination of the peak area will be very difficult using the 2 previous data processing tools. Computer integration systems, such as the PeakNet software that comes with the Dynex DX500 system, allows more accurate peak area calculations for these problematic separations.
Every brand of data processing software works differently, so it is not worthwhile to go into too much detail here. You should consult your user's manual for the specific details of your system. There are a few basic approaches used to process peak areas. First, when baseline resolution is achieved, the integration process is relatively straightforward. Tick marks are sometimes used to show where the system starts and ends integration. But what happens if you have what appears to be baseline resolution, but the baseline of the chromatogram has been elevated as shown here?
How will this affect the peak area? One possibility is that the integrator will redraw the baseline between the tick marks and ignore the area between the projected baseline and the true zero. Another possibility is that the integrator will include the area below the first baseline of the peak. This can result in significant errors in the calculation of peak area and subsequently compound concentration if the baseline elevation is not consistent with the calibration standards and the sample peaks.
Another important use of integration software packages is integrating shoulder peaks. This can be done in a variety of ways. First, the integration marks can be placed here in the complete area under the curve included in the integration. Another option would be to use the same tick marks, but estimate the baseline as the curve that the larger peak would assume if the shoulder peak were not present. A straight line could also be used. Note the difference in the shaded areas. Since we relate peak area to concentration, the integration method used will greatly affect the calculated concentration. Another option is to use the peak height method, but this is also the subject of each of the concerns mentioned earlier.
High-performance liquid chromatography has become easier, faster, and more automated with the aid of computers. With successful selection of the mobile and stationary phases, a larger number of separations are being achieved and more confirmatory compound identifications are being made.
Prior to startup of the HPLC, there are a few items to prepare. First, one must select and prepare the solvent gradient to be used. The proper solvent gradient can usually be obtained from the column manufacturer or from the technical applications assistant from your brand of the HPLC. These contacts will also be useful in selecting the appropriate column to be used. You should also have your calibration standards ready before you turn on the HPLC.
There are 4 basic steps to start the typical HPLC. Turn on all power switches. On the Dynex DX500, there are separate switches on the auto-injector, pump, detector, interface box, and the computer.
Next, the solvent must be filtered as shown in an earlier demonstration and placed in the solvent reservoir holder and degassed with the helium.
Then the pump must be primed. There are 2 ways to prime the Dynex pump. The automated method involves starting the pump. We will use a flow rate of 1.0 milliliters per minute. Next, open the bypass valve. This valve takes the flow from the pump effluent and sends it to the waste container, thus bypassing the injector and column.
When the prime button is pressed, the pump will increase the flow rate and remove any gas bubbles in the system. To stop the priming process, press the prime button again and close the bypass valve. If you have more solvent reservoirs that will be used, repeat the process. First, you must switch from solvent A to solvent B on the pump control panel. Again, open the bypass valve and press the prime button. Note the gas bubbles exiting the system. Each priming step will take approximately 30 to 45 seconds. When you are finished priming the pump, set the flow rate to the desired flow rate for the analytical method.
The system should be allowed to stabilize with respect to solvent composition for about 20 minutes prior to use. This will also allow the detector to warm up and stabilize.
To shut down the system, exit the software controlling the HPLC. Turn off the detector. This will conserve the life of the lamps. Next, turn off the pump, and if necessary, adjust the pump from computer control to manual control. Switch the solvent source to the washing solvent. This is usually methanol, but may also be deionized water. Prime the pump, as shown earlier. Adjust the flow to 1 to 2 milliliters per minute and allow the system to run for about 20 minutes to flush out the system. Finally, turn off all switches and clean up the work area. If there are multiple users of the system, remove your guard and analytical column, cap the ends, and store the column. You may also want to remove and store your solvents.